Have you ever stared at a page of your professor's notes and felt completely lost? You see all these terms, TCP dump, promiscuous mode, BPF, and it feels like you're trying to read a different language. Well, don't worry. In the next few minutes, we're going to decode all of that together. We are going to make the invisible world of your network visible. So here's our game plan. We'll kick things off with the big picture, what packet capture even is, then we'll look at the tools of the trade. After that, we'll dive into the really smart ways to filter all that data, how to actually listen in on a network, and why having a fast machine is so critical. By the end, I promise all these pieces are going to click right into place. All right, first things first. Before we get into any of the fancy tools or the technical jargon, let's just take a step back and figure out what we're actually trying to do here. What is the main goal when we talk about network packet capture? Think about it. Right now, as you're watching this, there's a blizzard of data flying across your network, but you can't see a single bit of it. It is completely invisible. Packet capture is basically like putting your network under a super powerful microscope. It lets us see all those tiny individual packets of data so we can understand what is really going on under the hood. And that brings us to a huge term from your notes, full packet capture, or FPC. And honestly, it's pretty much what it sounds like. It's the process of recording everything. Every single data packet that crosses a certain point on the network. Just imagine setting up a high-speed camera on a digital highway to record every single car that drives by. That's FPC. Okay, so how do we actually do this? Your professor's notes call out two main tools for the job, and they really represent two totally different ways of thinking about the problem. Let's break them down. In one corner, you've got Wireshark. It's the heavyweight champ. It has this nice, user-friendly graphical interface, a GUI. And it understands a ridiculous number of network protocols, which are just the different languages computers use to talk. But in the other corner, you have TCP dump. It's just a simple command line tool, no fancy windows, no pretty graphs. But it is incredibly fast and barely uses any of your computer's resources. So the choice really comes down to what you need. The deep dive analysis you get from a GUI, or the raw speed and efficiency you get from the command line. All right, so we've got our tools. But capturing every single packet, well, that creates a brand new problem, doesn't it? How in the world do you find that one important piece of information in a massive ocean of data? This is where filtering becomes your best friend. And this slide just hits the nail on the head. A busy network, even just your home Wi-Fi, can spit out millions of packets in just a few minutes. Trying to troubleshoot one little problem in that absolute mess is, well, it's impossible. We're not trying to drink from a fire hose here. We need a way to narrow that fire hose down to just the few drops of water we actually care about. And this is where the magic happens. Meet the Berkeley Packet Filter, or BPF. Now, the most important thing to understand about BPF is where it does its job. It doesn't wait for all that data to get to your analysis tool. No way. It works way down at the kernel level, the absolute core of your operating system, and it throws away all the junk packets before your application even knows they existed. That is the key to its power. So, the big takeaway here is that because BPF filters so early in the process, it is unbelievably fast. It takes that chaotic flood of data and turns it into a clean, manageable stream that you can actually work with. You can write these super flexible rules like, hey, just show me the data from this computer and from this specific application, and it'll do it instantly. This means your computer isn't wasting a ton of time and energy processing data you were just going to ignore anyway. Okay, let's make this real with the exact example from your notes. This BPF filter is basically a set of instructions for TCP dump. It's saying, listen, I only want to see packets that meet three conditions. First, they have to use the TCP protocol. Second, they also have to be going to or from port 80, which is for web traffic. And third, they must involve the computer with the IP address 192.168.1.1. See how powerful that is? With one simple line, we've just told it to ignore millions of other packets and focus only on the web traffic from one specific machine. Now that we know how to capture data and filter it down, we gotta talk about how our network card is actually listening. It turns out it has different modes for different jobs, and knowing the difference between them is absolutely crucial. So, by default, your network card is in what's called non-promiscuous mode. The best way to think about this is that it's being polite at a party. It only pays attention to conversations that are directed specifically at it, based on its unique physical address, its MAC address. It just politely ignores all the other chatter in the room. This is the normal, everyday mode for all your devices. Promiscuous mode is the complete opposite. This is the full-on eavesdropping mode. You're basically telling your network card, forget being polite. I want you to grab a copy of every single packet you see on the network. I don't care who it's for. This is obviously essential if you're a network analyst trying to see what's going on. But on most modern networks, there is a giant catch. Pay attention to this right here. This is almost certainly going to be an exam question. See, back in the old days, networks used devices called hubs, which were kind of dumb. They just shouted every packet out to every single computer. But today, we use switches. And a switch is smart. It's like a clever telephone operator who knows exactly which computer is plugged into which port, so it sends traffic only to the intended destination. This means that even if your computer is in full eavesdropping mode, it's not going to see the traffic between two other computers because the switch never sends it your way in the first place. So if promiscuous mode is kind of hobbled on modern wired networks, what about Wi-Fi? Well, that's where monitor mode comes in. This is a special mode just for wireless cards. It lets the card just passively listen to all the raw Wi-Fi signals that are literally floating through the air around you without even being connected to a network. This is the mode you have to use for any kind of deep Wi-Fi analysis. And yes, for Wi-Fi hacking. We are almost at the finish line. This last section in the notes covers a really practical point. Capturing tons of network data, especially on a really fast network, is an incredibly demanding job. Your average laptop, well, it's probably not going to be able to keep up. So, for those high-speed networks, your professor's notes give us a recipe for success. You need a powerful, dedicated machine just to grab the packets. You're going to use a lean, mean tool like TCP dump, not the heavy Wireshark GUI, to make sure the capture itself is lightning fast. And then, you need some seriously fast storage, like an SSD, to write all that data down without falling behind. It's all about making sure there are no bottlenecks anywhere in the process, from the wire to the disk. Okay, deep breath. We have covered a ton of ground. Now let's boil it all down into the most important need-to-know points. Think of this as your personal cheat sheet for acing any test on this stuff. So let's lock this in. Full packet capture, or FPC, means recording everything. Wireshark is your tool for deep analysis. TCP dump is for raw speed. BPF is your secret weapon, that essential filter at the kernel level that makes it all manageable. And remember the big limitation of promiscuous mode on switched networks, and know that monitor mode is its cousin for the Wi-Fi world. And finally, don't forget, serious packet capture requires serious, dedicated hardware. Look, we've just unpacked an incredibly powerful toolkit for making the invisible visible. It's absolutely essential for network security and troubleshooting, but it also gives you the ability to see things that are deeply personal and private. And that leaves us with a really important question to think about. Now that you understand this power, where do you think we should draw the line between keeping our network secure and protecting our right to personal privacy?